The elements, a visual exploration of every known atom in the universe. Let's get this started with. This is the last element in the lanthanides table. I promise you it is the last one. This is number 71, lutetium. Lutetium, it is the most wonderful thing about lutetium, though. It's that it's one of the last of the lanthanide rare earth science series. I just told you that already. And it's the last of these. After lantanium, we go back to the dynamic regular periodic table of the whole body until we have to go back to the actinides. Then we're finally done until we make a new table someday. Now, why are all these rare earths so similar, you might be asking? Most scientists don't really know sometimes, but for so many years that they have been so interchangeable that many years that these mixtures won't really important to even discover. So the electrons in an atom of a particular shell are arranged in shells. And the weirdness of quantum mechanics is that if you're not even allowed to think of an electron as having an actual location, it's always changing it at mind-boggling speed. So it's always at a different place at a different time. It's never in one place. Once you measure where it is, you cannot measure its velocity. When you measure its velocity, you cannot measure where it is. If you measure something, you lose the information from another one. Yeah, chemistry is primarily the story of the outermost shell of the electrons, but that's not always what happens. Electrons have the same number of electrons in that outermost shell, tend to have similar chemical properties. However, this is the fact that this is the fundamental principle of all of these elements too. In most parts of the periodic table, when you move from one element to the next, you're adding a new valence electron each time, giving each new element unique properties. But in the rare earths range, electrons are being added to an inner shell instead. Every one of the rare earths have 57 to 71 has a full 6's outer electron shell and a differing number of the deep 4f shell. You might have noticed that they all have 6s full up, but they have a different 4f shell, which is why it keeps filling up. I mean, take a look at this. They always have the 6s full. That's their most outermost shell, but their 4f was increasing this entire time. That's kind of why they're all kind of unstable too. If no one else is going to give an element home though, the lighting industry always steps up. It's always going to use lutetium for its lighting stuff too. The lutetium bromide is lovely created to the highest standards of purity, and we use this for lighting things too. And other than that, though, there's not much else we can use for lutetium. It's worthless compared to other metals. So there's not much more to say about lutetium. So just go ahead, talk about its statistics. The atomic weight is 174.967. Its density is 9.841. Its atomic radius is 217 picometers. Its crystal structure, it's a hexagon. What did you expect? It has a substantially mid amount of melting temperature, and it has a substantially higher melting point too. It's about double of the height. And now we're starting to add a little bit on the inner shells. We're still adding in the inner shells, so unfortunately, and so here we are stuck with 5D. Such a long way until we fill that gap, and I don't think we'll ever fill it. So apologies to everyone if you see me a little bit insane by the end of this series. Regardless though, let's start talking about 72, hafnium. Hafnium by itself, it's a specialist. It does one thing, and it does it really well. In the past, cutting through steel required a lot of very high-tech torches, which was really hot and very dangerous to use. And it was connected to two heavy and potentially dangerous cylinders of compressed gas. And these days, though, you really need to cut steel with a completely self-contained plasma torch that doesn't need more than electricity, that has a standard 120-volt wall outlet and air around us. Yeah, you don't need compressed gas anymore. A plasma torch contains an air compressor, and you go ahead and heat it up to so extremes that it becomes ionized, so hot that it basically becomes lava. And then you release all that in a stream of electricity, and you use that to cut off the steel. When you pull the triggers, all the electrons initiate an arc from the hafnium button, and a stream of compressed air blows the arc plasma out of the tip to the torch and into the metal that you want to cut. Pretty much hafnium is one of the things that helps with all this. So why hafnium is the tip? Well, hafnium has a high melting point and is extremely resistant to corrosion, even at high temperatures. So it is able to withstand conditions of arcs for such an extended period of time. Yeah, hafnium can be used to create several different colors too, including like some sort of copper green, like the color of the Statue of Liberty. Hafnium cartride can also be used as an inserting bit, and you use it in those plasma colors I just talked about earlier. They're really beautiful to look at as well too. Its atomic weight is 178.49. Its density is 13.310. Its atomic radius is 208 picometers, and its crystal structure, it's a hexagonal prism. We're starting to fill up the 5Ds, but my sanity will probably not remain until the end of this series. Its atomic emission spectrum is more contained in the middle. Also, we still see some parts of it on the left or downside of it. It has an exceptionally high melting point, as I mentioned earlier, and it's an even more exceptionally high boiling point, which makes it useful as a steel cutter, the only one who can kill Superman, if kryptonite was not already chosen as its element of weakness. Here we go, tantalum. Tantalum is one of the 2 elements that have been boycotted or boycotts organized against them. People are urged to boycott other ones, such as carbon, because sales of conflict diamonds are said to be funding certain wars and support nasty local regimes where the diamonds are mined, which is nasty. As I mentioned earlier, gorillas are dying to fund guerrilla warfares and all for tantalum. Yes, we're killing the habitats of gorillas just to get mining for tantalum too. But why is tantalum so useful? So, it's useful in cell phones and electronic devices. You use them in there all the time. You need tantalum for those electronic devices. They're really, really important, especially in this modern age of technology and the internet, which will become better in the future too. The question is, how do you boycott an element when everyone is not even allowed to have a pure sample of it at most times? Tantalum is not limited in applications, just in name recognition. Not just cell phones, but computers, talking dolls, and other applications that have the name tantalum in them. They're just boycotted. And most of the time, they do contain tantalum inside of them as well, too. The advantage of tantalum is that you can always reduce the size of the capacitor and still have the same output, and that's how tantalum was created. Tantalum condensators are especially effective at absorbing and dampening noise spikes before they cause trouble. And yeah, noise spikes are terrible things to your phone, and they may even let your phone become exploded. But all the early diversity in light bulb filament material, including carbon, tantalum, and osmium, even platinum, fell by the wayside when it became impossible to manufacture tungsten wire, which I'll be talking about in the next element. But first, statistics. Its atomic weight is 180.9479. Its density is 60.650. Its atomic radius is 400 picometers. Its crystal structure, it's a cube. It has an really exceptionally high and a ridiculously exceptionally high melting point, and it's an even ridiculously higher melting point, boiling point as well too. So it's really rare to see this thing as a gas. 5D is starting to be filled up. I really want to fill that gap, but my sanity will not allow it. And next we have tungsten. You might see this coil of wire. You might be wondering what it is. It's a tungsten filament wire. It's the thing that's put inside light bulbs. Yeah, tungsten is overwhelmingly associated with one application, and that is incandescent light bulbs. Incandescent light bulbs are really useful for tungsten, mainly because tungsten is very heat resistant and will do, at least as most we can do, 100 kilowatts per hour of incandescent light bulbs too. Tungsten best is nowhere near good enough, so a typical incandescent light bulb is only like 10% of the electricity it uses in visible light. The other 90% is just used up as heat, so it's practically inefficient. God, you might as well call them heaters that produce a minor byproduct of light. When we want them to create light and we create a byproduct of heat, you should call them heaters. That's why heaters are really bright. So. If it's light that you want, you can always now use the super useful compact fluorescent light bulbs, which are several times as efficient as the incandescent light bulbs and will last so much longer. It even uses so much light, makes so much more light. The metals from tungsten through gold are very dense. Indeed, osmium and rhenium are the densest of all the elements, but tungsten itself, well, tungsten is the cheapest by the factor of all the 100, so that's why it's used. Tungsten's density is so compact that you even use them in air darts. And tungsten carbide is the most common material for cutting bit inserts. That's very useful for tungsten, but you might be wondering, why is the elemental symbol W? Well, that's because tungsten's other name, German name, was Wolfram, and well, the Germans named it. Its atomic weight is 183.84. Its density is 19.250. Its atomic radius is 193 picometers. And its crystal structure, it's a cube. Once again, from now on, most of these metals will have a ridiculously, exceptionally high melting points. And this one, it has an even more ridiculously exceptionally high boiling point. The electron filling order, it's starting to fill up a bit more, and my sanity really pleads for this whole thing to be full. Its atomic emission spectrum, though, it's kind of hazy. When I mentioned about tungsten, though, it's really tough, and we even use them for leads. This cannot be cut with unconventional tools, and yeah, when you get one stuck on your finger, what's the best way to get it off of you? Apparently the answer is vice grip tools. You have to crack it open, you cannot cut it open. Without, well, risking cutting your skin. Next up, we have rhenium. Rhenium itself is the last stable element to be discovered. Last stable element to be discovered in 1925 in Germany. It was probably discovered in 1908 by Japan, but, well, the Germans get the credit. And it might be known as Nipponium if only Ogawa had not been sought. If not only Ogawa had not sought and claimed that he had discovered the element directly above it too, the element of the periodic table, element of 43, which we now know as technetium. Elements in the same column of the periodic table go ahead and share many similar characteristics. So Ogawa found an element that seemed very similar to manganese, but was heavier. It was quite reasonable to him that he thought it must have been element number 43, a well-known hole in the periodic table. And it was just in the right place, too. Sadly, though, he was wrong. Technetium, the real element 43, is radioactive and does not occur in nature, something no one would have guessed in 1908. Who would have guessed that in 1908? Many years have passed after rhenium's discovery rhenium's discovery, and eventually the stuff became very expensive. Like, we're talking about several $100,000 per troy ounce, and you know how big a troy ounce is? Well, just imagine it at least. Imagine it even smaller than an ounce, a fraction of an ounce. Most rhenium is used inside the nickel-iron superalloys that we have nowadays, and you can go ahead and use them in spinning discs of tungsten rhenium alloys. And when you strike them with a high voltage, well, you get electrons in an X-ray tube. In fact, it's used in X-rays as well too. Rhenium foil strips are used in evaporation filaments and mass spectrometers, such as the one that we see here, the atomic emission spectrum. That's all I can say about this, though. Now we are going on ahead and talk about its stats, and that's it for today. So its atomic weight is 186.207, its density is 21.02, its atomic radius is 188 picometers, its crystal structure is a hexagonal prism. Once again, it has really high, and I am not even going to say ridiculously, it's overrated. It's a really high melting point, but this one, it's ridiculously high boiling point. Yeah, there you go. I can only say ridiculously. 5D is trying to be filled up. I really hope 5F is filled up all the way. And that's it for today. I hope you guys enjoyed this episode of the periodic table of elements. I'll see you guys soon. Until next time, Shanana, peace. Bye-bye!